Hi everyone, today in this video I'm going to turn Solo into a servo drive. We're going to learn how to set up the whole system, how to tune the controllers, and more importantly, how field-oriented control works for controlling the position of a brushless or generally a three-phase motor. If you have any question or doubt after watching this video, you can come to our forum, you can post your questions, and absolutely we're going to answer them all. Right now in this tutorial I'm going to use this motor, which is a brushless AC or permanent magnet synchronous motor, but the same method can be done with Solo using brushless DC motors or Coreless EC brushless motors in exactly the same way. So today my focus will be on this particular type of brushless motor, and as you see, I've done the wiring of the motor, I've done the wiring of the encoder, and as a matter of fact, the type of the wiring you do is important. It's important how you connect the encoder, and it's important how you connect the motor to Solo. And to learn about this, you can go to our website. We have a tutorial on that, and we're going to have a video also on that. Just a little bit of time to tune everything, and then finally calibrating the encoder, which is again done completely automatically in Solo. The only thing you need to do is just connect the wirings in a proper way, and that's it. Today, I'm gonna use only digital control. That's why I'm using the USB cable, and this will be actually the only way that I'm commanding to Solo. So we have the USB cable to send the commands through the motion terminal. We have the power supply right here connected to the motor and nothing else. The motor itself and the encoder is connected. The encoder I'm using for this particular type of motor is from the type of an incremental types of encoder, which has 1000 slits and actually 3 pulses, 2 pulses that are normal quadrature pulses and 1 pulse for the index, which indicates the 1 turn rotation. And it's actually necessary for brushless motors controlling for Solo. So I've done all the connections, and before going to the details, I'm just gonna show you how Solo behaves, how this control is done in the first part of this video. And once you saw how it behaves, we're gonna go to the details. I'm gonna explain you how actually this thing works and what's happening behind the scenes. So let's just start it. I'm just gonna turn on Solo. So now I'm just gonna get connected to Solo, and I'm gonna just show you what actually will happen considering the fact that I've already set all of these parameters that are necessary for position controlling, and I'm already in digital mode. If you're in analog mode, you need just to go to digital mode and in position mode. So every parameter is set. I'm just gonna show you what happens when you send the desired position in a quadrature manner to Solo and what will happen. To show you what really will happen, I'm gonna activate the monitoring mode in performance mode, and I'm gonna just show you the parameters that I'm interested in for now, which will be the speed and the position. So here is the monitoring mode, and now I'm gonna ask Solo just to go for me in a positive direction into 1 million pulses. So let's see what happens. I'm gonna put 1 million pulses, quadrature pulses, here as my goal, and I'm gonna ask Solo go all the way from 0, which is now, to this part. So let's see what happens. I set it, it goes all the way up, and actually it reached to this 1 million pulses from 0 through this beautiful green line going up and reaching to 1 million pulses. So here is the goal. There is a little bit of error, but it's really low. And then here we have the speed, which is kept constant at 5000 RPM. Why is it 5000 RPM? Because we asked Solo to do so. So this is the speed limit that we said, okay, go to this, let's say, reference with this speed. And it did it. So it went from 0 to positive 1 million pulses, and it kept the speed at 5000 RPM. I'm gonna keep activate the performance mode. Now I'm gonna tell to Solo, okay, go to minus 1 million for me now, from the position you are here. And then it's gonna do that. It's gonna go down all the way to minus 1 million pulses. And again, you see that here, we're in positive 1 million pulses. I go all the way down through this very straight line of the position to minus 1 million pulses. And you see that the speed is kept constant. When you are near the target, the speed slows down, it starts to decay in a very, let's say, controlled manner. So when you are approaching to the goal, it understands that, okay, you're close to the goal, and it starts to reduce the speed, and then when you reach the goal, speed practically becomes 0 and it keeps you at the goal. So that's pretty much everything. Okay, now I'm gonna play a little bit with this. I'm just gonna show you a lot of different conditions. I'm gonna say to Solo, okay, now you're at minus 1 million pulses. This is where you are now, but I'd like you to go to another reference, which will be maybe positive 3 million, but I'm gonna ask you to go with 3000 RPM first of all, and then this will be your goal. Now you're gonna go to 3 million, but in the meantime, I'm gonna apply some torque on the motor, and let's see what happens. So it started to go up. I applied a little bit of torque by my hand. I'm just gonna be a little bit annoying. I'm just gonna force it to resist in front of my hand and see what happens. What actually happens, it's trying to reach the goal, and this is actually not the best practice, but I'm just gonna play with this a little bit. And then you see that these are the moments that I'm applying torque on the motor with my hand. The speed is actually trying to keep around 3000 RPM, but due to the fact that I'm applying torque, there will be a little bit of disturbance. It's actually within the range, it's acceptable for me, for my application. But if I activate the torque plot, it will be very much clear that what happened. Actually, what's happening, that the moments that I'm putting and applying some torque on the motor, that are increasing the current, and it's trying to keep the speed constant by increasing the torque, which is happening here in these parts of the plot, in the blue parts. And when I suddenly release the load, there is a little bit of overshoot, but again, it stabilizes itself. So that's it. That's the whole point of this control. I can try to, for example, irritate it while it's steady at these 3 million pulses. I'm gonna just turn it by my hand, but it goes back to the goal. You see that I'm just turning it by hand here, but it doesn't actually stays there and immediately goes back to the goal. So these are the things that you can play with. It's really easy. It's really nice also to set it up and play with the parameters to learn how it works. Now I'm gonna a little bit go to the details, how you can actually set the thing up and make it work for you in position mode. So let's do it. Just to go a little bit deeper on what we want to do here, I'm going to show you this diagram, which is the main diagram of field-oriented control type of things that's happening in Solo. It might look a little bit strange or maybe complicated to you, but don't worry, we're not going to go so deep in this. We're just going to talk about the main philosophical reasons that we're using the same control in our system and how you should proceed with that. It starts with the motor at the most exterior part, and it goes all the way back with all the controllers and the sections. The sections that we are interested today on are located at this part of the diagram. So it's basically decomposed out of two parts. The first part is the controller parts are dealing with torque, speed, and then finally position. And then there is another part which is dealing with the magnetizing current for AC induction motors, or the intensity of the field of the stator, or flux control for other types of brushless. Basically, we are most interested in the first part. And as you go on with Solo, you need to tune one after the other these controllers. So firstly, we will start with the torque controller, which is the first controller that is actually automatically tuned after you run the motor identification. And then there are other controllers like speed, which is tuned after the torque controller, and then there is a position controller which is tuned finally. So you need to tune them one after each other, starting with torque, going to the speed, and then finally tuning the position controller. If you don't want to use the position controller, for example, you just need to tune the speed controller, and the torque controller, of course, is tuned automatically. And also for testing, it's the same. You start from the most interior part, which is the torque controller, you test it, then you go to the speed controller, you tune it and you test it, and then finally you end up with position controller, and once you tune it, you can test it. So if one of these controllers is not tuned, for example, if the speed controller is not well tuned, probably it will affect the position controller, it will affect the next controller. You always need to make sure that all of these controllers are working well together, and sometimes you need to go back again and tune backward and go back again and tune forward. So it's just kind of a little bit of a playing with the system to see how it behaves, and then finally, once all of them are tuned, it's gonna work really good. Okay, now actually we're gonna see what happened behind the scene, how I could achieve this control, how I could set up everything for my controller and the motor in a way that I could control the position in that way that you saw in the beginning of the video. So to start with that, you need to start with the configuration part, including the PWM frequency, which is the output switching frequency at the output. So I found that for my motor, 30 kHz is working pretty good. This frequency, this switching frequency, depends on the inductance of your motor. So if you're using a low inductance motor, you need to have higher values here, all the way up to 80 kHz. And if you're using motors with higher inductances, you probably need less switching frequency. For my motor here, I found 30 kHz is a good value. It's very stable in this frequency and it works good. The next thing you need to set up is the current limit. So for my motor, again, 12 amps is a good current to act all the way in continuous mode and also in transient mode, because you shouldn't put this value very low, because you need sometimes to have a little bit of current in your motor to start up, to go after the position, and then increasing the speed while there is a little bit of disturbance, increasing the torque, and so on and so forth. So this current limit actually is something that depends on your application and of course on your motor. For my motor, this value is fine. My motor has 8 number of poles, and remember, number of poles is different with number of pole pairs, because number of pole pairs is half of this value. So my motor has 8 poles, which is the number of magnets on the rotor of this motor, this type of brushless motor. Of course, you need to select the motor type. My motor type here now is Brushless EC or permanent magnet synchronous motor. I'm using the normal type because this motor is actually not super fast, so I'm using this type of motor. And finally, you need to set the encoder lines, which is actually known as encoder slits. In my case, it's 1000, which means my encoder on this motor has 1000 hole engraved for each pulse. So once I do all these settings, I'm here, I can do the motor identification, but before that, you need to make sure that Solo is in closed loop mode. The only analog setting that you need to apply is this. We're not using any of these analog inputs, we're not using these potentiometers. We just need to make sure the pin number 5 of Solo is down. This means you are in closed loop mode, you're not in open loop mode. Because in open loop mode, you're not gonna have position or torque capability. You can only control the speed, but that's not in our interest, and we're just gonna want to put this controller in closed loop mode. So once it's in closed loop mode, you can run the motor identification. There will be a little bit of vibration, and then the motor will be identified. This actually is the first loop, which is the torque controller loop, which is automatically tuned now. So as I said earlier, now we have the torque controller tuned. We can test it now. So the next step is calibrating the encoder in this part. But since I've done the wiring of the encoder and the wiring of the motor, and at that part I've also done the encoder calibration, which is saved into the memory of Solo. I don't need to do it every time, and I have the calibrated values here, so I'm not going to change them. I'm not going to run again the calibration. We have a good article about this on our website, and we're going to make a video for that. So for now, I'm going to leave this out, and I'm going to just go straightly to the control part. So the very first thing I'm going to check after this part is the first loop, which is the torque loop, and I'm interested to see if the torque loop is actually well tuned automatically here. So what I'm going to do is this. I'm going to go to digital mode, because I'm using only digital mode. I'm going to go to torque mode, which is good. I'm going to make sure that this speed or torque control mode is selected on encoder, because when you are in position mode, it automatically goes into encoder mode. But if you are in a speed or torque mode, actually you have 3 options. You have sensorless option, you have encoder option, and you have Hall sensors option. So now my case of interest is torque mode in using encoders. And I'm gonna make sure that after I give a torque reference, if everything is well managed and everything is set up in a good way, I need to see that my motor is reaching to a nominal speed of this motor. While I give a torque reference here, is actually accelerating from 0 speed to the nominal speed, because I'm just the motor is just freewheeling and not gonna apply any torque on it at the moment. So I'm gonna put 1.5 amps as a torque reference, and I'm gonna see that if this motor actually can go to the nominal speed of itself with this amount of current. I'm not applying any load on it, so 1.5 amps should be enough, and I'm gonna see that. I'm gonna just send this value, and actually I'm gonna just follow a little bit here, maybe just getting rid of these parameters. I don't need to know the position for now. And yeah, you see that actually the speed is in the nominal speed and the torque is actually within this value. The torque is not 1.5 amps because there is no load on this motor. But if I actually try to do a little bit of a tweaking here, if I grab this shaft of this motor, which is easy now because there is a very low torque on the motor, you see that the torque remains exactly at 1.5 amps. It's negative because the direction of the rotation is clockwise. If you go to counterclockwise, I'm going to see that the torque goes from negative values to the positive values. And again, if I keep the shaft here steady, I see that the torque is positive 1.5 amps. This shows that actually torque controller is working good. So I'm not having any worry about that. I'm just gonna jump into the speed controller and tune the parameters there. So I'm gonna go to the speed controller. Again, I'm making sure I'm in encoder mode. The speed controller is actually something that you have to tune it yourself. So I'm starting from 0 values, let's say for both of the speed controller KP and a speed controller KI. And I'm gonna make sure that the parameters are 0. Now I'm going to just put a value out of my feelings. For now, I'm not going to push this too hard. So I'm going to put 0.05 here for the speed controller KP and a much smaller value for speed controller KI for now, and see what happens. So basically, speed controller KP defines for you how fast you want to reach to the reference and how much forceful you want to reach to that. And speed controller KI is defining if you're going to have 0 steady state error during the time, and actually is a little bit a slower gain, but it's going to accumulate. So you need to be careful not to put so high values here. So I just put these two experimental values here. So I'm going to tell to my motor to go to 1000 RPM, and I'm going to just send this value to the motor and see what happens. I set to go to 1000 RPM. The motor seems working good. Yeah. And here you can see that the speed from 0 just rose slowly to 1000 RPM. The speed plot is actually going very nicely up from the 0 speed all the way up to 1000 RPM, and it doesn't have any overshoot. It's going actually smoothly up, but I'm going to make sure that it can actually sustain a little bit of torque. So just this motor is small, so I can grab it a little bit by my hand, and it seems resistive. It's resisting against my hand, and I can also verify here that while I am applying load on the shaft, it tries to resist in front of my hand. Maybe I need to increase a little bit this value. Maybe I go to 0.08 just to be a little bit more forceful, and then I'm gonna again go back here and see what happened. It seems better. It seems a little bit better. It's fighting against my forces. Maybe I reduce a little bit the KI. Maybe I don't need so much high value there, but no, actually it made it worse. So it shows to me that, okay, maybe I need to go a little bit higher here, and I need to have some value like 0.1 maybe. It's going good now. I'm happy with it. So maybe for now I leave it like that. Then I'm gonna see the effect in position control mode. But you see that the speed is kind of followed in the reference. It's kind of steady there. Okay, now after setting up my speed controller and making sure that everything works well, I'm gonna go to the position controller. But before that, please make sure that the position value you're in before going to the position controller, is not really high values, because if you immediately go to the position controller and you set up the first gain, it's going to go back all the way to the 0 for the position reference, and that's not going to be good. So to make sure that that's not going to happen, just turn off your solo and turn it back on. So we're gonna make sure that we are starting from 0 in everything. Just the first time, just for the setup. So after you go to the position mode and it's gonna stay there in the memory, you're not gonna do anything else. So I go to digital mode again. I was in a speed mode. I've done all the tunings. I'm not worried about anything else. I'm just gonna go to the position mode. So I can see that the speed control values are set from the values I set before. And now I need to set the position control values. Again, I'm gonna put 0 here and 0 there for the position controller. So I'm gonna start from this. Normally, the gains of the position controller are a little bit higher than the speed controller. So maybe I put here 0.1 for the KP of a position controller and 0.02 for the KI. KI is essential to have a zero steady state error. So the next thing I'm gonna set the speed limit, which defines for me the speed of the trajectory that I'm gonna traverse. So for me, 3000 RPM for now is fine. So before running anything else, I'm gonna go to the performance mode and I'm gonna just leave the speed and torque for me just to have some plots here. So now the first thing I'm gonna ask Solo to go to 50,000 pulses and I'm gonna see what happens. Is it good? Is it bad? Can it do that or it cannot do that? So yes, it seems it could do it, but it seems that the motor is a little bit not stable in let's say steady state. So there are some pulses here, but the motor could actually go from 0 value of the position to the requested value of 50,000, but it's not really good. So what we need to do is we need to go back and we need to set our parameters. I'm gonna just increase a little bit the KP value to 0.15 and maybe a little bit of more KI, which I'm gonna put it on 0.08 and I'm gonna see what happens actually after setting this value. So let's see how Solo traverses to a position like minus 1 million pulses in a quadrature manner. So I'm gonna see how we go there. I'm gonna send this value and I'm gonna observe it here. So it's going smoothly with 3000 RPM and there is a little bit of vibration in zero steady state, but it's not that much. It's really not annoying, but anyways, I'm gonna increase maybe a little bit the gains of the KP and see how I can reduce this effect. So actually by increasing it, it made it worse. So maybe I need to reduce it to this value, 0.12, and maybe I can have a little bit of less speed control KP just to make sure the whole thing is better and stable. Seems now is much better. So I'm gonna go again back to positive 1 million pulses and let's see what happens. There is a traversing of the speed is good actually. So I'm kind of having a steady speed at 3000 RPM and going all the way up to the desired position. So now I'm going to check if I can turn the encoder. I can turn it, so it means that the gains of the KP of the position control is not really high. I can maybe increase it a little bit. Maybe I can go to 0.2 and see how is the behavior. Seems a little bit better. Maybe the gain of the KI is too much, so I increase it a little bit. I'm just putting every possible way for you here just to see. I'm not having a better response because it's jumping. I reduced it, maybe it's becoming better, maybe 0.08. So seems that's how we have it. So maybe I'm gonna have a little bit of more KI. So it's actually, now it's pretty stiff, it's not moving really easily, and I can kind of control it in a good way. So let's go to minus 1 million pulses. It's going in a good way. So we can play more with all of these values. We can play more with speed controller values. Maybe, for example, if I increase this speed controller KP to a much more aggressive value, let's say 0.1, I see that I don't have those steady state errors. It becomes much less. And if I go back to positive 1 million, I'm gonna see, yeah. So So now we can, for example, during this transfer, let's reach to 1 million pulses, and I'm gonna change the speed in the middle of the traversing. So I'm gonna go to 5 million pulses. So it starts to move, and then I'm gonna change the speed. I'm gonna go to 1000. You see that the speed dropped to 1000. I'm gonna go back to 5000, and the speed jumped up to 5000. And then I'm gonna have different values, but now I'm there at the goal. So to do that, I can go minus 5 million pulses, and I can again change the speed to 1000 RPM again and see actually how it works. You see that the speed dropped to 1000 RPM actually, and the position controlling is slower, but it's going through the whole process to reach to the goal and actually is working. So that was the whole process of setting up your motor. Basically, you need to tune two controllers. You need to tune the speed controller and the position controller, and beside all, you need to be sure that the wiring you're applying to the motor is correct. Thank you so much.